Just so you all know, the recording's about to start now.
Okay.
Okay. You can't let it be silent, but if you want people to hear you, then. Hi everyone. So let's just give this a minute for people to join, and then we'll start. Okay, so let's get started. So at the end of last class, we talked about Chebyshev's inequality, right? So last class, we ended last class with a discussion on Chebyshev's inequality. Okay, and so I stated Chebyshev's inequality, and there are two versions of it. So I'm going to show you last class's notes. So I think you could see that, because this was last class's notes. And so we had Chebyshev's inequality here, right? Okay, so we had all of that from last class. Okay, so this was from last class. Let x be a random variable. If e of x squared is finite, then for any positive c, you have the probability that the absolute value of x is greater or equal to c is less or equal to the expected value of x squared over c squared. And then we have these two inequalities here. Okay, let x be a random variable of finite mean mu and finite variance sigma squared. For positive constants d and k, we have these two inequalities. Okay, so these two are both called Chebyshev's inequality. So we're going to start today's class with an example that uses Chebyshev's inequality. So this is example 6.25. When a certain speed control device is set at m miles per hour, the actual speed in miles per hour of an automobile equipped with this device. Okay, I'll put on the recording. Oh, it is recording. Okay. Hello. Okay, with this device is a random variable capital X with mean mu which equals m and standard deviation sigma which equals 3. If the device is set at 45 miles per hour, with a 50 mile per hour speed limit, what is the Chebyshev's estimate of the probability that the speed of the automobile will exceed speed limit. Okay, so it's a very long, wordy problem. Sorry about that. Okay, so let me read it from the beginning, on the top. When a certain speed control device is set at m miles per hour, the actual speed in miles per hour of an automobile equipped with this device is a random variable x with mean mu equals m and standard deviation sigma equals 3. If the device is set at 45 miles per hour with the 50 mile per hour speed limit, what is the Chebyshev estimate of the probability that the speed of the automobile will exceed the speed limit? Okay, so solution. Okay, let's assume capital X is a continuous random variable. Okay, so X here is defined here, right? You have a random variable X with mean mu equals m and standard deviation sigma equals 3. Okay. So let's find the probability that the actual speed exceeds the speed limit. Okay, so that's equal to the probability so that's equal to the probability that x, which is the actual speed, is greater than 50. 50 is the speed limit in miles per hour. Okay, so that's equal to the probability that x is greater than or equal to 50. Because since it's a continuous random variable, you can include x equals 50 and it doesn't change the probability of the interval. This is less than or equal to the probability that the absolute value of x minus 45 is greater than or equal to 5. Okay, so why is that? So okay, so let me go to the whiteboard real quick. So what we're looking at is this probability, right? Saying that this probability is less than or equal to this one. So on the whiteboard, let me show you something. So if you have x, right, and let's say this is 50. And so if you're looking at the interval x greater than or equal to 50, get this interval. Okay, this is x greater than or equal to 50. Now, if you look at the interval of, now let's look at the x values that satisfy x minus 45 is greater than or equal to 5. So what that interval is it's saying that the distance from away from 40, x is at least 5 away from 45. Well, here's 45. If it's at least 5 away from 45, then that means that it could actually be less than 45. And so it could either be this, or it could be this. And so the values of x that satisfy the inequality x minus 45 greater than 5 are all the x values at least 5 away from 45. This distance is 5. This distance is 5. And this is 40 here. And so the blue intervals here and here, these are the x values that satisfy this, and the red is the x values that satisfy this. So you see that the x values that satisfy this inequality is a subset of the x values that satisfy this one. So the probability, that means that the probability that the absolute value of x minus 45 is greater than or equal to 5 has to be greater than or equal to the probability that x is greater than or equal to 50, right? Because these x values are all of these and more, right? And so this probability should be greater than that one. This includes all of these and more. Because this is the x values that satisfy this is a subset of the x values that satisfy that. This probability has to be greater than that one. Okay, you can see that there. So that's what we get here, that this is less or equal to that. Okay, and so that's the explanation for that. Now this is equal to the probability that x minus mu is greater or equal to 5. Right? Because here we're setting it at 45 miles per hour. So we're setting the mean mu to be 45 miles an hour. So mu here is 45. And so by Chebyshev's inequality, we have that this is less or equal to so by the corollary, we have this, that here's the d, right? D is positive, mu is positive, and so this is less or equal to sigma squared. Sigma squared is 3 squared. It's less than or equal to 3 squared over d squared. D is the thing here. D is the 5. So we're squaring 5. Less than or equal to 5 squared. 5 squared. So see, it's just a simple matter of plugging into the corollary. Okay. And so this is equal to 9 over 25. And that's equal to 0.36. Okay. So the probability of the actual speed exceeds a similar speed limit is at most less than or equal to 0.36. And so this was by corollary to Chebyshev's inequality. Okay. Okay, so that's the end of that section. 6.7. That's all 6.7. So 6.8 is titled Means and Variances of Special Probability Distributions. Okay. So let's start with example 6.26. The probability a person is infected by a certain disease, is 0.05. If 1,000 people are exposed, what is the expected number that will become infected? Okay, so solution. Let capital X equal the number of people infected. Okay, so X is a binomial random variable with probability P, which equals 0.05, and N, which is the number of people, is 1,000. So the expected value, the mathematical expectation or expected value of capital X is E of X, which equals N times P, which is 1,000 times 0.05, which is 50. Okay, so you can expect 50 people to be infected. Okay. Okay, probability is 0.05, and the 1,000 people are exposed. So you multiply the number of people times the probability of being infected, and that's the expected number of people you would expect to get infected. Okay. Example 6.7. If the distributions of raisins per cookie is Poisson with lambda equaling to tau, what is the expected number of raisins per cookie? Solution. Okay, let X equal the number of raisins per cookie. And so it's a Poisson random variable with parameter lambda equaling to 4. Then the expected value, E of x, is equal to just lambda, which is 4. Okay? So when you have a Poisson random variable, the expected value is lambda, which is 4, the parameter. Okay, so the parameter is the expected value. And since you're given what the parameter is, it's tau. Oops. Wait, that is a 4. Okay, sorry, lambda is just 4. So the expected value is 4, right? Okay, so you can expect 4 raisins per cookie, okay, because x is a Poisson random variable with parameter lambda equals 4. So lambda just tells you the expected value. Very simple. Okay, example 6.28. If capital X is the amount of soda in ounces per cup dispensed by a dispensing machine, then f of x is equal to f of x is equal to 1 if 6.5 is less than x less than 7.5, and it's 0 elsewhere. Okay, so the PDF f of x shows that capital X is a uniform random variable with parameter alpha equals to 6.5 and beta equal to 7.5. Therefore, the expected value here is just alpha plus beta over 2. Okay, which is the same as 6.5 plus 7.5 over 2. That's the same as 14 over 2, which is 7. Okay, so when you have a uniform random variable, you just take the average of these two values. That's 6.5 plus 7.5 over 2, which is 7. 14 over 2, 7. Okay, so you can see how in each of these examples we have a different formula for the expected value. N times P here, lambda here, average here. Okay, it's very simple. And then next is example 6.29. If the length of phone calls in minutes arriving at a certain switchboard is a random variable capital X PDF probability density function f of x, which is equal to 1/5 e to the negative x over 5. Okay. And this is for x greater than 0. This is for x less or equal to 0. And so it has that PDF. What is the expected length per call? Okay, solution. X is exponentially distributive. Okay, so it has a PDF of the form of an exponential PDF, which means it's an exponential random variable x, which means x is an exponential random variable. And so its parameter is just the 5 here, right? So note that the PDF for an exponential random variable is of the form, and it looks like this: f of x is equal to 1 over theta e raised to the negative theta negative x over theta. And this is for x positive, and then 0 for x less or equal to 0. So the PDF for an exponential variable with parameter theta is of the form if f of x equals this, right? So you see that the theta here is 5. So here the parameter theta is equal to 5. It's just thing here and the thing here. Okay. Therefore, the expected value of x is equal to theta, which is 5. Okay, that tells us that the expected length of individual calls in minutes is 5. Right, and so that's it. So theta for an exponential random variable tells you the expected value. Okay, and so that is 6.8, the mean and variances of special probability distributions. Let's keep going. 6.9, standardized random variables. So 6.9.1 is on related theorems. Theorem 6.8. Let capital X be a random variable with mean mu and standard deviation sigma. If y is equal to x minus mu over sigma, then the expected value of y is equal to 0, and the variance of y is equal to 1. Okay, so the proof of that is just if you have your expected value of y, this is the expected value of x minus mu over sigma. So then you take the constant 1 over mu out. So you have 1 over mu e of x minus mu. Oh, sorry, the sigma here. This is sigma. 1 over sigma e of x minus mu. And so this is equal to 1 over sigma times e of x minus mu. Okay, because e of x minus e of mu, which is mu. And well, e of x is mu. So this is mu minus mu here, and so this is 0. So I show this e of y is 0. And then as for the variance of y, the variance of y so the variance of y is equal to the variance of x minus mu over sigma. But that's equal to, by an earlier formula, 1 over sigma squared times the variance of x minus mu. Okay? So as a reminder, if you take the variance of ax plus b, it's equal to a squared times the variance of x. Okay, so here the a is the 1 over sigma, and so it's 1 over sigma squared times, and here the variable is x minus mu. Just put just variance of x here. Okay, and so then that's equal to, well, the variance is sigma squared. So you got sigma squared divided by sigma squared. Because the variance of x is sigma squared, so sigma squared root of sigma squared is 1. And so I show that the e of y is 0, and the variance of y is 1. So that proof is done. Okay, so notes, a random variable with mean equal to 0 and variance equal to 1 is in standard form. The random variable x minus mu over sigma, therefore, is in standard form. And is called the standardized random variable corresponding to the random variable capital X. So given any random variable capital X, you can standardize it by defining a new variable as x minus its mean mu over its standard deviation sigma. So x minus mu over sigma is the standard form of that random variable x. Okay? The standardized normal random variable is called a standard normal random variable. Okay, so when you have a normal random variable and you standardize it, it's called the standard normal random variable. Theorem 6.9. Let capital X be a random variable whose distribution is normal with mean mu and variance sigma squared. Let z, which equals to x minus mu over sigma, z is standard normal. So Z is standard normal because it's of this form. Okay, so that's the theorem. 6.9.2. Computing probabilities for the normal random theorem. So theorem 6.9 allows us to use the table 3 in Appendix C. That's the table in on Blackboard. I put on Blackboard. Okay, to compute probabilities for normal random variables. Okay. The reason is because if we're given a normal random variable, we can write it in standard normal form and then find probabilities of the corresponding standard normal random variable C. Okay? We did that before. And so that theorem allows us to do what we did before. Okay. So let capital X be a normal random variable with mean, mu, and variance, sigma squared. To find the probability that A is less than X less than B, use theorem 6.8 to write right? So we have this theorem here. So we start with the probability of A less than X less than B. This is equal to the probability that A minus mu over sigma is less than X minus mu over sigma, which is less than B minus A over sigma. So what I did was I just took each of these AX and B, I subtracted them by mu and divide by sigma. And so it does not change the direction of these inequalities. And so the X values that satisfy these two inequalities are the same as the X values that satisfy those two. So these two probabilities are the same. It's asking for the probability of the same set of X values. And so this is equal to the probability that, so you have these two inequalities here. But this variable is a new variable we defined as Z. So it's really the probability that Z is here. And so Z is a standard normal. C is standard normal. It's a random variable. So we may use table 3 to find the desired probability. Okay. And so the theorems we just discussed allow us to do that. Okay. Example 6.31. Let capital X be normal with mean 1 and variance 4. Find the probability that 2 is less than X less than 3. Okay. So if we want to find the probability that 2 is less than X less than 3, that's going to equal to the probability. So you're going to have this here, except the A is 2 and the B is 3. The mean is 1. So you're subtracting each of them by 1. Oh, wait, here? It should be a mu here. That's a mu right there. This should be a mu. All right. So then, so you subtract 1 there, and you divide by sigma. So the variance is 4, right? But sigma is the square root. Remember that the variance is equal to sigma squared, right? And so that means that sigma here means that sigma squared, which is the variance, right? The variance is sigma squared. Means the variance is equal to sigma squared, which equals 4. So that means that sigma is equal to 2. Okay, sigma squared is 4, so sigma is 2. And so here in the denominator, you divide by 2, not 4. That's the trick. Okay? That's where the problem can mess you up. Okay, so now this is equal to probability. So 2 minus 1 over 2, that's 1/2. So that's probably 1/2 less than z. Right, z is this guy, less than 3 minus 1 over 2, that's 1. So you want the probability z is in that interval. And so if you use the tables in Appendix C, right, then this is going to be equal to this is going to be equal to the probability that 0 is less than z less than 1. Probably that 0 is less than z less than 1 minus the probability that 0 is less than z less than 1/2. Okay, and so you use the table in Appendix C, you plug them in, and then you subtract, and you get 0.1498. Okay, so right here's the table, right? So, so in the problem we have 1 and 1/2 here. So you subtract 1, 1/2. So it's this value minus this one. It's 0.3413 minus 0.1915. Right? Get that. You just plug in the values in the table and subtract, and you get that. Okay, 6.10. More applications. So estimating the means of distribution. Distributions. Okay, so applying the strong law of large numbers, we have the following method. So if capital X is a random variable and x sub I is the ith observed value of capital X, then the strong law of large numbers says that the sum of all those values of X So the sum from I equals 1 to n of x sub I over n is approximately mu with great probability n is large. Okay, so when n is very large, it's very likely that if you add up the observed values of x and divide by how many times you observe them, that ratio should be very close to mu. Okay. Okay, so now we're in the last chapter, chapter 7, which is on multivariate distributions. So we're going to go to 7.2, which is on multivariate distributions. 7.2.1, which is on multivariate probability functions. Definition 7.1. The multivariate probability function of discrete random variables x1, x2, up to including x sub n, is the function defined by f of x1, comma x2, comma dot dot dot, comma x sub n, which is equal to the probability that x1 is equal to little x1, x2 is equal to little x2, up to including xn is equal to little xn. For all possible values, x1, x2, comma dot dot dot, comma x sub n, x1, x2, comma dot dot dot, comma x sub n, respectively. Okay, so what this function's saying is f of all these variables, little x1, little xn, it's the probability that your discrete random variables, capital X1, capital Xn, or have these corresponding values, little x1 to little xn. Okay, so this is the probability that capital X1 is little x1 and capital X2 is little x2 and dot 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 and capital Xn is little xn. Okay, so it's before we found the probability that a random variable was a particular value. Now we have a probability function that tells you n variables have n values. Okay, this is the probability that each of those n discrete random variables have correspondingly each of those n lowercase x values. Okay, example. Example 7.1. And so here's the experiment. Rolling a die and then tossing a coin. Rolling a die, tossing a coin. That's the experiment. X1 is the value on the die, and X2 is the number of heads. Okay, find the joint probability function of X1 and X2. Okay, so first an observation. the events x1, x1 and x2 are independent events. Okay, so they are independent events. And so therefore, the joint probability function of x1 and x2 is so P of x1 comma x2 is equal to the probability that x1, the probability that x1 is equal to little x1 and x2 is equal to little x2. Well, since events x1, x2 are independent, the occurrence of one either has no effect on the occurrence of the other. So the probability of them both happening is the products of their separate probabilities. So this is equal to the probability that capital X1 equals little x1 times the probability that capital X2 is equal to little x2. That's because capital X1 and capital X2 are independent. Okay, so now it's a matter of finding what these probabilities are. But the first event, X1, is a value on a die, right? And so the probability of X1 assuming any value on the die would be 1/6, right? Because there's 6 values on the die. And then X2 is the number of heads. Well, X2 is number of heads, right? So what is the probability of each number of heads? So you have, if you toss a coin, the options are heads or tails, right? So there's a 1/2 chance of getting 0 or 1 heads, right? So it's 1/6 times 1/2, which is 1/12. And this is for x of I being 1, 2, 3, 4, 5, 6, and sorry, x1 being that, and x2 being 0, 1. Okay. Okay, so then you have that. Okay. All right, and so that breaks down to the product of them two because they're independent events, x1, x2. Example 7.3. Let capital X equal to the number of outgoing local calls. And let X equal the number of outgoing local calls. And let Y equal to the number of outgoing long distance calls. Okay, this is both during a 5-minute period. Joint probability function of capital X and capital Y is given by the following table of values. Okay, so okay, so you have 0, you have do it this way. 0, 1, 2, 3, and 4. So then you have here 0, 1, 2. So these are y values, and then this column are x values. These are x values over here. Okay, on this side, and these are y values. Okay, so I'm just going to fill in this table. This is 0.23, 0.23, 0.11, 0.04, 0.01, 0.11, 0.11, 0.05, 0.02, 0.01. And the third row is 0.03, 0.03, 0.01, 0.01, 0.00. Okay, so we have this table of values, right, that tells you the probabilities of each combination of x and y values, right? So the probability that x is 2 and y is 2 is 0.01. That would be an example, okay? And so this table, this defines the function f of x comma y, okay? Okay, so part A, the question is, what is the probability of exactly 2 local, 2 long distance calls? Okay, x is local, y is long distance. So x2, so this is equal to the probability that x is 2 and y is 2. Okay, so we have that probability. So what is the probability x equals 2 and y equals 2? It's 0.01. That equals 0.01. See right there, this value right here. So that's A. B, the probability of more than 3 outgoing calls. Okay, so what is the probability of more than 3 outgoing calls? So outgoing calls, so x is local, y is long distance. So it's really the probability that x plus y is greater than 3, right? So you want the sum of local and long distance outgoing calls to be greater than 3. So you just find all the ways that could happen. That could be f of 2 comma 2, the probability that x is 2 and y is 2. 2 plus 2 is 4, plus f of 3 comma 1, plus f of 4 comma 0, plus f of 3 comma 2, plus f of 4 comma 1, plus f of 4 comma 2. Okay, so I'm just going to put the plus sign over here. Okay, And so now you plug in. So f of 2 comma 2 would be 0.01 plus f of 3 comma 1, which would be 0.02 plus f of 4 comma 0, which would be 0.01 plus f of 3 comma 2, which would be 0.01 plus f of 4 comma 1, which is 0.01 plus f of 4 comma 2, which is 0.00. Okay, so you get 0.06. And that's it. So the probability of more than 3 outgoing calls is 0.066%. Okay, C, what is the probability of no outgoing local telephone calls? Okay, so the probability of no outgoing local telephone calls is f of 0 comma 0 plus f of 0 comma 1 plus f of 0 comma 2. And so that's equal to, so again, you refer to the table, f of 0 comma 0 is 0.23 plus f of 0 comma 1 here, which is 0.11, plus f of 0 comma 2, which is 0.03. And so you add them up and you get 0.37. Okay, because x is the number of outgoing local calls. And so this is the sum of all the values when x is 0. 0, 0, 0, 1, 0, 2. See, x, these are all the ways that x could be 0. You add them up. Okay, so that's that example. Let's keep going. 7.2.2, which is a multivariate cumulative distribution functions. This is definition 7.2. The multivariate cumulative distribution function of the random variable capital X, random variables x1, x2, xn is the function capital F defined by capital F of x1, comma x2, comma comma x sub n. This is equal to the probability that x1 is less than or equal to little x1, capital x2 is less than or equal to little x2, comma comma capital X sub n is less than or equal to little x sub n for values. For the values of each x sub I, where each x sub I is between negative infinity and infinity. Okay, and this is for I from 1 to n. Okay, if two random variables are involved, the multivariate cumulative distribution function is called the joint cumulative distribution function. Okay, so let's do an example. Consider the random variables x and y of example 7.3. So the example we have right here, this table. Okay, find capital F of 2 comma 1. Okay, so capital F of 2, 1, okay? By the definition up here, it's the probability that the first variable x is at most 2, and the second variable y is at most 1. Okay, see that? See the x1s, xn's, they're just the probabilities that the capital X's are at most those little x's. Okay. And so according to the table, that value is going to be, well, if x is at most 2 and y is at most 1, you can see you're just going to add up these 6 probabilities here. So it's going to be f of 2, 1 plus f of 2, 0 plus f of 1, 1 plus f of 1, 0 plus f of 0, 1 plus f of 0, 0. That's equal to. So, right, so again, by the table, which is now over there, back here, okay. So right, so x at most 2 and y at most 1, we have these 6 values here. 2, 2, 1, 2, 0, 1, 1, 1, 0, 0, 1, 0, 0. So you add up these 6 values, you're going to get 0.05 plus 0.11 plus 0.11 plus 0.23 plus 0.11 plus 0.23. Just add up these values. Okay, so I'm going to write that down here. So this is 0.05 plus 0.11 plus 0.11 plus 0.23 plus 0.11 plus 0.23. And you add up those numbers, you get 0.84. Okay, so that's explaining how to calculate the value of a cumulative distribution function in that example. Okay, so the next section is 7.2.3, which is on the multivariate probability density. It's on multivariate probability density functions. Okay, so this is, let's start with the definition. This is definition 7.3. So continuous random variables x1 to x sub n are jointly continuous if there is an integrable function little f such that the probability that x1 is at most little x1, x2 is at most little x2, comma, x sub n is at most little xn. Well, that's equal to the integral from negative infinity to xn the integral from negative infinity to x2, the integral from negative infinity to x1 of f t1 t2 comma t sub n dt1 dt2 dtn. This is for x values, finite x values. So x abide between negative infinity and infinity. This is for I equals 1, 2, 3, up to including n. Function f is the multivariate probability density function of the random variables. Okay. Okay, so this is defining what jointly continuous random variables are. And so it says there's an integrable function at little f such that the probability of this is equal to these iterated integrals. Okay. And so this is like the cumulative distribution function, except for multiple variables. Before we had a cumulative distribution function, it said the probability of a random variable being at most value. Now this is the probability of little n many variables, each being at most their own corresponding value. So x1 is at most this, x2 is at most that, up to including xn is at most that. It's probably all of those n variables are at most their own corresponding values. Okay, and you integrate to get that. Okay, so it's defined there. When two continuous random variables are involved, the multivariate probability density function is called the joint probability density function of the random variable. Okay, and so when there's two involved, it's called the joint probability density function. Okay, some important facts. Okay, by definition, 7.3, if x and y are jointly continuous random variables with joint probability density function f of x, y, then one, the joint cumulative distribution function of x and y is capital F of x, y, which is equal to double integral from negative infinity to y, and the integral from negative infinity to x of f of s comma t ds dt. This is for negative infinity less than x less than infinity, and negative infinity less than y less than infinity. Okay, so if you have a joint cumulative distribution function of x and y, then it's of this form, where you have just two integrals here, right? This is for n, but now this is for two. Okay, joint means two of them. Okay, the second point is that for values a1 less than capital X less than b1, and a2 less than y less than b2, probability that A1 is less than X less than B1, and A2 is less than Y less than B2 is equal to the integral. Oh, there it is equal to the integral from A2 to B2, and then the integral inside the integral from A1 to B1 of f of x comma y dx dy. Okay, because x is going from A1 to B1 and y is going from A2 to B2. Okay, the third point is that if C is a region of points x comma y in the plane, and P of x comma y belong to C, the probability of the point x comma y belong to C denotes the probability that the random variables x and y take on the respective values little x and little y, so that the point x comma y is a point in region C. So if all that happens, then the probability that x comma y is in C is equal to the double integral over the region C of f of x comma y dx dy. So the integration is over region C, and probability only defined if the integral exists. Or if f x comma y is the cumulative distribution function of x and y, and the joint probability density function is given by the function x comma y, the joint probability density function is given by the second derivative. The second derivative of capital F of x comma y dx dy. d2 capital F dx dy. At all values x and y, where the partial derivative is defined. Okay. These four statements can be extended to more than two jointly continuous random variables. Okay, so we'll stop there. Stop there. Okay, so we can stop there. Let me just see something. Okay, so are there any questions about homework 8? So any questions about homework 8? So this was homework 8. Okay, so this was homework 8. Are there any questions about any of these problems? These 6 problems? So let's just look at one of them if there's no questions. Let's look at 6.3.2, this one. Find e of x squared, e of x to 1/2, and e of 2x to 1/2. So this is the problem. Let's see if I can just copy and paste it here. Okay, so this was the problem, though I don't think the formatting is gonna, oh, maybe it did, sort of. No, it didn't. Never mind. I can't copy and paste it. Okay, so you have the assignments. So I'm going to refer to it. So if we look at number 1, this is our PDF. So let's find e of x squared for this, okay? I'm going to alternate back and forth. So e of x squared, right, is equal to the sum of all possible values of little x of x squared f of x. And so what is that? So the possible values of x, the possible values of x are 1, 4, and 9. So it's 1, 4, and 9. So we have 1 squared times f(1) plus 4 squared times f of 4. This is 1 squared plus 5 squared times f of 5. Okay. So you just calculate that. So 1, 4, 5. 1, 4, 5. 1, 4, 9. Okay, the corresponding probability is 0.1, 0.4, and 0.5. 0.1, 0.4, 0.9. This is 9. Okay, so now you plug in. So you get 1 times f of 1. F of 1 was, what was it? 0.1, 0.1, 0.4, and 0.5. So you have 0.1 plus 16 times 0.4 plus 81 times 0.9. 0.5. It's 0.5. Let me check again. 0.1, 0.4, 0.5. Okay. So then you just calculate this. So this is 0.1 plus 7.2. 16 times 4 is 72 times 1 times 7.2 plus 81 times 0.5, which is 40.5. Okay, so you add up those values and you get 47.8. Okay, and so e of x squared is 47.8, and so that's one of the calculations of that problem. The other ones are just very similar, right? You just do a similar thing here, and you can find these other two. So this was one of the problems. If there's no more questions, I guess we can stop there. Okay, so I'm just going to assign another homework though. So the homework due for Monday is the following. So okay, so we have homework 9. Okay, so homework 9 and homework 10 are due Monday. Homeworks 9 and 10 are due Monday. Okay. Okay, so homework 9 and 10 are due Monday because that's 6.2 past that. Okay, and let me just check something real quick. You have 7 points. Oh, okay. So then I guess that's what it would be. Okay. So wait. Where am I? Okay, here. There's multiple screens going on my screen. Okay, so homework due for Monday is homework 9 and 10 due Monday, right? So I already announced I announced everything about the exam, right? So let me just put this on the screen again. Okay, so here, right, the final is on the 17th, right? Okay, and test 2 is on Wednesday, May 12th, right? Okay. Okay, so I'm going to copy this. I'm going to put it on today's notes. So all this also, test 2, remember, this is a reminder, and this is now an important reminder. This is a reminder now, okay? So reminding you that the final is on the 17th during class, the last day of class. It covers all the semester. The review sheet is on Blackboard, okay? And I'll return your test 2 grades after you take it and before you take the final. Okay, so when you take the final, you know all your grades. Test 2, again, is on the 12th. Starts at 8 o'clock during class. Okay, review sheet for test 2 and the final, they're both on Blackboard. Okay, any questions about anything? Okay, so I'll see all of you on Monday. Bye. You're welcome. Have a good night.
Good evening, Professor. This is Karul Fahim.
Hi, how are you?
I'm doing well. How about you?
Doing good. What's up?
I just want to say something after everyone leaves.
Okay.
Sure.
Okay, so I'm going to stop the recording.